right. Yeah, thanks. Yeah, thanks for inviting me. I'm excited to talk about my research on the interplay and of stochasticity and nonlinearity. And when I was asked to give this talk here from the technical committee of vibration and sound, I thought, okay, I might as well try to address both audience, so the people who care about vibrations and those who care about waves. So that's how the title came up with. And in the first part, I'm primarily going to talk about vibrations to entertain half of the audience, and then we're going to venture into waves to entertain the other half of the audience. If you care about both, I hope you are entertained throughout the whole talk. This primarily the research was done during my postdoc at the University of Maryland in College Park, and I recently transitioned to University of Wisconsin-Madison, where I got the joy of teaching for the first time. So that also brings me to the motivation of this talk. So let me tell you a little bit of a personal story. So I recently got into the joy of teaching undergrad vibration classes here at UW-Madison. And I like it. It's a beautiful topic. I torture students with those spring mass systems. Sometimes I throw dampers in, sometimes I leave them out, a little bit of forcing here and there. But it's a nice topic. You can derive. You have closed form solutions. You can do simple derivations on one page. You can have beautiful plots. You can explain pretty much anything that's going on. And so essentially, what I'm teaching students is linear deterministic vibrations. And while I think it's fun to do for its own sake, and students might not always agree with that so much. So to get students entertained, at least for the beginning, I show a lot of videos and pictures about vibrations. So we talk about classical structure vibrations of bridges, Tacoma Narrows Bridge, Millennium Bridge. I show videos of an excessive vibration in the laundry machine. A little bit about timekeeping, how every timekeeping relies on the vibration from pendulum clocks all the way down to quartz or even atomistics clock, which measure transition times, vibrations in molecules. And I show them flutter vibrations or fluid structure vibration, galloping of power lines. And that keeps students motivated for quite some time. So they still attend my lecture, so I'm very happy about that. However, I'm always a little like, yeah, I always feel a little like a hypocrite, because I mean, if you really look at those things, let's take the pendulum here. So timekeeping, we know if we have this is a pendulum clock. If we have for certain amplitudes of a certain displacements, we see that we know that the frequency of the pendulum clock becomes amplitude dependent. So this is a prime example of a nonlinear system. Or if we go to microscales here, so timekeeping at microscales, noise aspects, especially phase noise, is a huge thing. So there already we see that in this simple system, we already need to talk about nonlinearities and noise. Similarly here, what happens here, why this thing is the laundry machine is getting destroyed, is essentially what they do in the beginning. They throw in a piece of metal and then they let it run. And I mean, this is we have continuous contact between this rattling piece and the machine, and contact is a highly nonlinear phenomena. Similarly, if we talk about here this flutter vibration or galloping, this thing is at rest in the beginning, and then certain parameters, environment, wind speed changes, which then gives rise to self-excited oscillations, which then go to a limit cycle. So this is a prime nonlinear example again. And if we now think about that the wind speed is most likely not going to be constant in the real application anymore, but might be a very complicated field, we might talk about the stochasticity there as well. So in most of this example, I try to motivate linear deterministic vibration theory. We actually should have also talked about nonlinear and non-deterministic or stochastic aspects. And so what can we do if we have now noise and nonlinearities in our system. I mean, first thing which seems to work out quite well for many applications, we can just follow the route of my lecture and simply ignore it. All right, we just hope nothing. The noise and nonlinearities are small enough, and we can just fly through with our linear vibration theory. On the other hand, we can also deal with it. Okay, we accept now that we have nonlinearities, we have noise, everything gets a little complicated. But maybe I can design everything that our system performs also accordingly. Although we have those two players in the field. But here in this talk, I want to go a step further. So I want to look into I want to ask the question, can we now use noise and nonlinearity, exploit them for a beneficial interplay? And what challenges us to do that? So computations get very expensive. So we don't usually have closed form solutions. So we need to do a lot of numerics. And those needs to be coupled with probabilistic approaches, so a lot of sampling. So this is a very high intensive computations we need to perform here to study this interplay. And similarly, if we talk about experiments, we need accurate modelings. And also because we are talking about stochastic experiments, you run an experiment once, you have one sample. But if you want to have a meaningful conclusion, you want to draw a meaningful conclusion, you have to repeat this experiment over and over and over again until you have reached to you have a reasonable estimate of your quantity of interest. And so one thing I was particularly interested is the interplay of nonlinear resonance and noise. So here we studied a nonlinear oscillator. And if you are familiar with nonlinear oscillations, you know that what for certain system we observe region of bistability or hysteresis. So where we have a certain excitation frequencies here, we can observe that we either have very high amplitude vibrations or lower amplitude vibrations. So that's the deterministic picture. Now, what happens if we add noise into the game? So what then can happen that due to the noise terms, that we can observe transitions from the high amplitude orbit to the low amplitude orbit, or vice versa from the low amplitude orbit to the high amplitude orbit. And those transitions I wanted to look into a little bit more closer. And I wanted to we conducted an experimental and computational study to study these transitions a little closer. And the experiments were laborious, but more or less straightforward. So what we had a nonlinear oscillator set up, thanks to a grad student, Abdurrahman at the University of Maryland, who built the whole who worked on that. I think prior generations of PhD students have built that up. And I was fortunate to take over this experiment and just write the LabVIEW code, or like program the LabVIEW code. And so what I did, I just tell the thing, okay, sweep into the bistable region, and then we turn in noise. We switch on the noise. And that's here a very typical vibration pattern we can observe. So in the beginning, we turn on noise. The vibration pattern stays pretty much unchanged. So we are still somewhere close to the high amplitude orbit here. However, then then we observe that after a certain time here, around 58 seconds, that we now drastically and very quickly, the amplitude drops from this high amplitude orbit to a much lower vibration pattern, which is then close to this vibration amplitudes here. And this phenomena is called escape. And the time when this thing happens is called the escape time. And okay, this is now one sample, and we have repeated this thing over and over again to get an estimate of the escape time. So for this experiment, I did that for about 200 samples. I rerun the experiments over and over again. And to come up to accompany this experiment with some computations, we had to come up with a model for this setting. And of course, if we have a nonlinear force response curve in this form, we can fit a Duffy model to that. We can do that. That's not a big deal. However, now if we look a bit more closer here at the response at a very high or higher amplitude pattern, so I think at 39.6 Hertz, so somewhere up here, take a Fourier transformation of the response, we see that in the experiments we have a dominant second harmonic. But in the numerics, if we just look at we just simulate a Duffing oscillator, we don't see a second harmonic. And to account for this effect, to have a more accurate representation of the whole thing, we added a quadratic term, which then alleviates, at least to some extent, the inaccuracy of the model. And having done that, we were able to study those escape times. And so for the setting I was looking into, we had an escape time of an average about 20 seconds. And now this was an escape time for the white noise model. White noise model is not realistic in practice. So in reality, we're going to face some other noise model. And so we wanted to study different noise models. And one thing we can think about is, for example, band limiting the white noise. So we band limited the white noise between 2 and 100 Hertz. The natural linear frequency of the system was around 30 Hertz. And if we do that, the mean escape time increases by almost a factor of 1/2, so 50%. If we look at the pink noise model, so where the intensity is frequency dependent, then we see that there's a drastic reduction of the mean escape times. Whereas if we have another frequency noise model, the Brownian noise, where the intensity is also frequency dependent, here seen on the right hand side, we see about that the mean escape time has not changed much compared to the white noise case. So this shows that depending on the noise model, this can have an impact on the escape times we observe. So this the underlying noise model impacts the interplay we observe on the nonlinearities and stochasticity. Having finished the study, I was a little bit dissatisfied with this hand arguing of massaging a quadratic term into this equation for the nonlinear resonance. So I thought about maybe we can come up with a much more systematic approach. And so we have worked a little bit more on the system identification part. And so the goal was, now we have this type of measurement, so nonlinear force response curve, and we wanted to use this measurement to obtain governing equations. And I'm not going to go into the details of how we exactly did that. So just to draw it, so to summarize the key concept, we did modeling in the Fourier domain, polynomial expansion, and then subsequently performed the sparse regression to come up with a simple and easy model that accurately represents the measurements. If you're interested in the details, I recommend, or I can point you to the paper, or you can also I've uploaded a tutorial onto YouTube. You can go online and watch me explaining, going to the steps of explaining all the details of this procedure. Or you can also look at the code. It's published. You can use that. So the whole procedure is automated. And just to show you what comes out for this type of measurements, so we have this kind of measurement. And the model is quite simple. So it's just it's no like abstract interpolation concept which we cannot really write down. It's just a simple set of equations you can write down on a piece of paper and take next door to your colleague. The terms are also, we can at least relate physical sources to them. So we have damping, we have nonlinear stiffness and external excitation. And of course, we represent accurately the measurement. So beside now, this is essentially to some extent fitting. So you're wondering, so how general or how universal is the model we captured? And to test that, what we can do is we can just study this type of. So we can now vary the right-hand side. So we can vary the right-hand side, the forcing level in the experiment, and we can also vary the forcing level in the simulations. And if we now look, do the simulations and the experiment for different force levels, we get the different curves here. We have used the yellow one for fitting, so that was the data I showed you earlier. And if we now evaluate everything for other forcing amplitudes, we see that we still, at least to some extent, capture the with this model what's going on in the experiment. Only for very large vibration amplitudes, we see a deviation. Also, there are some effects we have not captured with this kind of excitation amplitudes. We can go a step further and think about, okay, I'm going to not only consider purely sinusoidal forcing. So what we've done, we also considered sine sweep, free decay, or random excitation. And overall, the story is very similar, so that the simulation and the experiment match very well. So that translates now to, if we have identified the model here with a, let's say, a sinusoidal excitation, we can now exert this model to different type of environments. And it seems to, at least for these environments I have tested, that the model still generalizes to these excitations. So you might wonder if the whole thing also works for a little bit more complicated systems. So that's what we have done here. We've considered a 3 degree of freedom structure. So these are 3 oscillators which are coupled. We have 3 resonance peaks between 30 and 45 hertz. And if we apply this procedure to this data, we come up with a model which consists of conservative terms, damping terms, and coupling terms. The coupling terms are linear in this case, and also we have forcing. And if we simulate these equations, we get back our the measurements quite accurately. As the last test, we have looked into 2 degree of freedom structure with an internal resonance. So internal resonance are inherently tricky to capture analytically, computationally, and also experimentally. So that's why they often serve as a benchmark in nonlinear system identification. One thing to notice here, so for example, this is the measurements we obtain. And so this, the upper branch here and the lower branch, they're called the main branch. And in addition to those 2 branches, we now see 2 detached branches, which are called isolars. No matter what the system is, if we just throw in this data in our procedure, we come up with simple equations of motion, where we can relate conservative terms, damping terms, and coupling terms. And simulating these models, these accurately capture the measured force response curves. So so far so good. This is all my experiments and my method. So I have the freedom of obtaining as accurate or as many measurements as I need to get the procedure working. Can we also, what happens if we don't have complete freedom of choosing our observations? So can we do this also for external data sets? And the answer is yes. So I've worked with jointed structures. So Matt Brake at Rice University is interested in jointed structures, and they have published some data sets. I can identify equations of motion for those kind of vibration setups. Curved structures and printed beams for Matt Allen, now BYU. I've worked with this kind of structures. NIST had a force sensor. They were interested in obtaining equations of motion, and also other structures with Hannover University back in Germany. And by all means, I still have some space on the slide. So if you have a nonlinear force response curve and you're interested in want to obtain some equations of motion, feel free to reach out, and I'm happy to discuss. So now we have a very accurate, systematic way of obtaining equations of motion, and we are back now in play of studying the interplay of the equation of stochasticity and nonlinearities in experimentally. And here I'm showing you a force response curve, now the interplay of nonlinearity and stochasticity. So this is the linear response. So this is just some system with linear FRF we are all familiar with. However, now if we add nonlinearity, we might observe this behavior, so hardening behavior, where the force response curve leans to the right. We have this bistability region. If we look now, for example, at the largest vibration pattern amplitude, the vibration amplitude has not changed much. Maybe went down a little bit, but not really significantly. If we add noise to the system, we kind of shift this force response curve a little bit up, but overall it remains more or less unchanged. Now the interplay, what happens in the interplay is the green curve. So we see now that the maximum vibration amplitude is drastically reduced. So this is essentially, this can function as a vibration attenuation strategy or vibration damping strategy. So the interplay of noise and nonlinearity can be leveraged to reduce vibration amplitudes. And just to explain you the underlying phenomena that's going on, I have to zoom into the region of bistability a bit more. And so here in this region of bistability, we have this high amplitude orbit and the low amplitude orbit, which are both steady state responses of this nonlinear system. And to understand what's going on, it's a bit easier to picture the whole thing as a potential system. So a potential system with two wells, where the one well represents the one steady state and the other well represents the other steady state. And now if I add noise to this picture, what happens? We now see that we see transitions. So if a system starts at one attractor here, it transitions to the other one and vice versa. But overall, the time it takes to transition from one to the other and the transition from A to B versus the transition from B to A is about the same. So overall, the system spends on this side the same amount of time as it spends on the right-hand side. However, in reality, potentials are usually asymmetric. And now if we have asymmetry, it turns out that the time the system needs to transition from this attractor to that attractor is much, much longer than the time it's needed to transition from this attractor to that attractor. And the whole thing becomes the design principle, or can become a design principle, if you can engineer your system such that here the attractor with the lower valve is your favorable operating point. And this turns out to be the case for this nonlinear resonance, where the lower branch turns out to be a much more favorable, or turns out to be an operating point which is favored by the stochastic terms. So the noise terms, they push you away from the high amplitude orbits towards the low amplitude orbit. So even if you start at the low amplitude orbit, you quickly drop down to the low amplitude orbit, and even if you start at the low amplitude orbit, you stay there, and it's very unlikely to escape to the attractor B, to the high amplitude orbit. And so we have tested this for single degree of freedom systems. So this is the hardening response. This is a softening response where we see a vibration reduction of about 50% in terms of the maximum amplitude here. We also have looked at multi-degree of freedom system. And the interesting thing is with this vibration strategy, or the vibration damping strategy, we don't really have to tackle each resonance individually. We don't have to tune mass damper for each resonance, or come up with a vibration control strategy for each and every resonance. It automatically tackles all involved resonances which are nonlinear. So we see that also for the multi-degree of freedom system, we dampen the response of all three resonances automatically. And the whole thing also worked for the for 2 degree of freedom with internal resonance. Is the sound still okay? I just disconnected my headphones, but if you can still hear me, I'll continue. If not, I'll try to fix that.
We can still hear you.
Oh, I cannot hear you.
Mm-hmm.
All right, are we now good on track?
We can hear you.
Okay,
Thomas.
perfect.
Can you hear us?
Great,
okay.
Yeah.
Okay.
I
great.
just disconnected my headphones. All right, we are good.
Right.
Back on track. This was the first half of the talk. So this is the vibration side. So where we have worked in the vibration setting, we have the system here interacts with the environment due to some external forcing, and then we see a response. So this is the classic vibration picture. And in the next part, I want to venture on to the waves topic, and where I work in a framework where things are much, much more uncertain. And for example, the governing equation of the system is not so clear, and also the external excitation is not so clear. And the waves I'm interested in are ocean waves. So for everybody who was hoping to hear something about sound waves, I'm sorry I lured you in. But I mean, you spent now 20 minutes in this talk, so you might as well finish it. So for the next 20 minutes, we talk a little bit about ocean waves. And so more specifically, what I'm interested in is extreme waves or rogue waves. And so what are those waves? So these are, so rogue waves are defined as waves which are significantly higher than their neighbors. So this is now here, this is an example of a rogue wave. We see that for the majority of the time, the sea surface elevation is rather limited. However, now here in this red window, we see that there's the wave is quickly approaching, which then is also quickly disappearing without any trace. And this is called a rogue wave. And without talking too much, just to give you a visual impression of the thing, here's the video on the right-hand side. This is a ship steering to the ocean. And as it is on its course, we can see here now on the right-hand side, we have a drastic, a large wave coming up to the ship and then eventually impacting. And just by seeing that, we can all, I hope you can see, you can imagine the pressure, the forces acting on the ship's hull. That's clearly not optimal. While this captain seems to be fine, and the ship seemed to be fine, at least no visible damage occurred. Others were not so lucky. So the loss of several supercarriers and also serious injuries of passengers and sailors have been linked to the occurrence of rogue waves. So this inspired quite some research in studying and predicting rogue waves. And so what I'm doing in the next, talking about the next part is data-driven forecasting. So what I want to do is we have some measurements of the past sea surface elevation, and based on that, I want to predict what's going to coming up, what are the next upcoming waves. No matter how we twist and turn the whole problem, we need data. And I found this data is provided by CDIP. CDIP is a program run by or financed by the Scripps Institution of Oceanography out of UC San Diego. And they provide a network of more than 160 buoys, primarily located at the coastlines of the continental US. And they record various sea state parameters, and that's what I'm interested in, is the wave height profiles. And if you stitch all the measurements together in all these buoys, 160 buoys, we have about 880 years of data sampled with a sampling frequency of 1.2 hertz. So I presume that the audience is used to work with much, much higher sampling rates. But let me tell you, 1.28 hertz is crazy high for oceanography. So oceanography, they commonly work in the time with sampling periods of half-an-hour intervals. So if you simulate, let's say, a sizable portion of the ocean, you do time stepping with half-an-hour time steps. So 1.28 hertz is unreasonably high for oceanography, but for this very specific wave topic where we have to capture individual waves, we need to have at least a sampling rate about of 1 second to resolve individual waves. So how do we do data-driven forecasting? And I'm sure you guys, most of you have read the news or are aware of the advent of machine learning approaches, which come with the promise that they can approximate any underlying functional approximation between data. So we can view now that the measurements of the path of the sea surface elevation and the future data as some kind of, and the model in between, we can view this as some sort of functional relationship. And so neural networks and universal function approximator should be well set to do the task now, based on to extract the patterns of the previous data or waves and then predict future waves. So we tried that out with various approaches, LSTMs, convolutional neural networks, transformers, feed-forward networks, and so on. And the story is pretty much the same, that the forecast deteriorates very quickly. So here, the red forecast has nothing to do with the actual happening sea surface, measured sea surface. So we had to do a little bit more. And so what we did, instead of going from the left-hand side, so from the past to the future directly with one big neural network, we had to do a little detour. And I'm going to talk to you about the detour, about the first two steps, the decomposition and the forecasting step, in the next couple of minutes. So after we failed with this straightforward or direct application of neural networks, we looked back into what is done in oceanography of modeling oceans. And so in the common models, the ocean is decomposed into a set of rapid oscillations with slowly varying amplitudes or spectrum, depends on who you ask. And this inspires the following model. So here, cosines or harmonic functions to model these rapid oscillations. And then we have some amplitudes. And these amplitudes are depending on these are depending on time, but they are slowly varying. So these are the slowly varying amplitudes of spectrum. And if you look at the model and you have done structural dynamics for up to then the rest, prior to this project, I've done only structural dynamics. You can imagine I was quite happy to see back just a bunch of Fourier modes. I can relate to that. Whereas oceanography, fluid dynamics, tedious, as a very complicated topic, very hard, very uncommon equations to me. So I was always joking after seeing that model. All right, I'm doing essentially structural dynamics of the ocean. And to use this model, we need to fit this to data. And we use the following cost functions. So the first term enforces that the model accurately represents the measurement, as is penalize the fitting error. And the second term is now enforcing slow variations in the amplitudes. And the second term now is scaled by a small parameter, which is then a hyperparameter, which one has to select. So we selected small so that even small variations are heavily penalized in this cost function. So by selecting a small parameter here, we penalize every amplitude variation quite drastically. No matter how you twist and turn the problem, the thing is still a nonlinear function. You need to do a nonlinear function optimization because the model here is nonlinear in the frequencies, and we don't know the frequencies. I'm not going to go too much into details how we performed the nonlinear function optimization, but we found a variable route to give us a workable approximate minimum within a couple of seconds. And now to do the forecasting. So given we have now fitted the model for, let's say, for 3 minutes, to do forecasting, I know we want to know what happens after 4 minutes, what happens after 5 minutes, and so on. So I need to evaluate this function now outside the fitting interval. So the harmonic functions are fine, the frequencies stay unchanged. However, I need to know the amplitudes. So I need to extrapolate now the amplitudes outside the fitting interval. And to do that now, we used our data-driven methods. So linear autoregressive models, or then neural networks with, so specifically recurrent neural networks with LSTM cells. Those methods are by Cora interpolation methods. So there's no guarantee that they actually work for forecasting. However, now if you look at what's done here, it seems much more promising to kind of forecast these slowly varying amplitudes versus extrapolating here on the rapidly varying sea surface. And that's what we observe in our experimentation, that this decomposition into slowly varying amplitudes extend the extrapolation range of our data-driven methods. So we have done ocean wave forecasting for various buoy locations, and we see that our methods were a bit employing neural networks with LSTM cells in the forecasting steps outperformed the relevant benchmark by about 25%. And we can also very accurately forecast large waves with this with employing neural networks. So remember back, I wanted to talk about, I motivated the whole thing about with rogue waves. And this is an example of a rogue wave. So we wanted to, so this is a forecast of a rogue wave 1 minute in advance. There's a good and a bad news, at least to me. So the yellow is the forecast. So yellow, we can see an increase and a decrease in the envelope. Which is correct. So this terms of correctly predict the rising and decreasing envelope. However, we see that the full extent of the rogue wave is clearly missed. So we have to do for rogue wave forecasting, we have to do a little more work. And just to give you a little bit of an overview over the field, what is done there. So rogue wave formation, there are two main theories. One theory is that rogue waves are formed by a superposition of elementary wave with random phases. So this is the model, looks very similar to the model we have discussed before, where the amplitudes and the frequencies are known, but the phases are unknown. Usually sampled with a uniform distribution on the interval between 0 and 2 pi. However, in this setting, because the phases are unknown, rogue waves are inherently unpredictable. So you might as well observe this sea surface elevation, but for another realization, you might observe a constructive overlay at a certain time instance, and then which gives rise to a large rogue wave. So in this setting, rogue waves are inherently unpredictable. So what we are set out to do to predict rogue waves is doomed to fail. However, there's another theory. This is called the Benjamin-Fair instability of the nonlinear Schrödinger equation. So can be shown that the nonlinear Schrödinger equation has a relevance for ocean waves. And this is a deterministic equation. And the Benjamin-Fair instability is a deterministic instability of this equation. And this occurs on a slow time scale. And I apologize. I think this video doesn't work. If you're interested, look at Google this publication. They have a nice video of a rogue wave approaching this ship. So according to this theory, the rogue wave is evolving very, very slowly over long time spans. And if that's were to be true, one could technically detect this growth in amplitude and predict rogue waves. So in this setting, so these primary theories of explaining rogue waves are conflicting here. So are rogue waves now predictable or unpredictable? And we took a very pragmatic approach to rogue wave forecasting. So remember, we want to answer the question: will a rogue wave occur? And now, if you give me this time series, this measurement of sea surface elevation, so basically now we have some knowledge of the sea surface elevation, and based on the knowledge of the sea surface elevation, we need to determine will a rogue wave occur in the future. And of course, for the top time series, there's no large wave coming up here, so the answer should be no, rogue wave will not occur. Whereas down here, we see a large rogue wave at about 35 minutes. In this setting, the answer should be yes, rogue wave will occur. And so if rogue waves are predictable, there should be some sort of functional relationship between the wave pattern happening before the rogue wave event and the rogue wave event. And if this functional relationship exists, we can approximate it with a neural network, which are universal function approximation. So this understanding of rogue wave prediction now turns my the forecasting problem into a time series classification problem. And it turns out that neural networks are much more designed and much more capable of doing those time series or classification problems than they are designed to do dynamic time series forecasting problems. And it turned out to work quite well. So with this approach, so we have here the confusion matrix. So this is this on this axis we have the the reality. So in truth, there was no rogue wave or rogue wave was coming up, and the prediction can also be rogue wave will come up or rogue wave will not become up or is not coming up. So overall, we end up with these 4 cases. And the beautiful quadrants are here, the true positive. So in this case, our model says, hey, rogue wave is coming up. And in the truth, also rogue wave did come up. So this is the number of accurate predictions. And we can see that we have 3 out of 4 rogue waves we can correctly predict with our neural network. Similarly here, this one is where there was no rogue wave coming up. But also the prediction says, hey, no rogue wave is coming up, which is also, again, about 75%. So the overall accuracy is about 75%, and only in 25% that is the truth and the prediction of the neural network. They don't agree. If you now think, this is an advanced warning time of 1 minute. So this gives you a warning time or warning horizon to perform safety measures of 1 minute. If you think, okay, in practice, we want to now extend this as much as possible. So we try to extend it, and then we see that the accuracy decreases slightly, but it decreases. So if you go all the way to 5 minutes, we drop the accuracy to almost 70%. Which is expected. So if you want to do longer forecasting, usually things get more complicated, as we do expect, and we also see the drop in accuracy. So once after we've performed this type of forecasting, once again we're wondering how universal is this? Is this a coincidence that it works for this data set? So how universal is whatever we obtain with this approach? And so this led us to experiment with this network on an unknown buoy location. So we have now excluded one buoy from the whole data set. So this buoy is off the coast of San Nicolas Island, close to LA. And this buoy, you see, over its whole time span has observed 350 rogue waves. And if we exclude this whole this data set from all the data we use for training and so on of the neural network, on the remaining buoys we see for the testing data, we have the accuracy of 75%. That what I have talked about previous slide. Now, if we evaluate the network on the unseen buoy data, we again observe an accuracy of about 75%. So that means whatever we have now captured with this neural network works quite well for other locations of the ocean. So technically, you can use this once trained network and deploy your buoy in front of your fishing boat or your wherever you are on the ocean. You operate your oil rig or whatever you're interested in, and use this network to forecast or to give you a warning of upcoming rogue waves. With this, towards the end of my talk. So just a summary, we have talked about vibrations. And the vibrations part, I have talked about automated identification routine and how we can utilize noise and nonlinearity for vibration damping. In the second part, waves, ocean waves in my case, we have utilized the decomposition strategy to decompose ocean waves into slow and fast components, train neural networks to predict rogue waves. With this, towards the end, I'd like to acknowledge all my coworkers during the time at University of Maryland, and also the sponsorship by through NSF to this to grants. So with that, I'm happy to answer any of your questions, to hear your comments. Yeah, thanks for listening.
Thank you, Thomas. Do we have any questions for our speaker?